Hey everybody, it's Joel Irway. What's going on? In today's lesson, we are going to be talking about Algebra of Complex Numbers Part 4, and with specific regards to polar coordinate systems. So without further ado, let's go ahead and get started. So the goal of this lesson today is to discuss the polar coordinate system and polar form of complex numbers in detail. And the overview of this lesson, first we'll discuss the details of the polar coordinate system. We're going to discuss when we would use the polar coordinate system, how we would know to use the polar coordinate system, and then walk through an example. We do have additional sample problems for you to download in the separate video section, so be sure to check that out. So the details of polar coordinate system. Well, the definition of the polar coordinate system is a two-dimensional coordinate system in which each point on a plane is determined by a distance from a fixed point and an angle from a fixed direction. Now, the fixed distance is represented by r, and the fixed direction is represented by theta, angle theta, which is measured with respect to the positive x-axis anti-clockwise or counterclockwise. Now, transformational rules. The relation between the rectangular coordinate system x and y and the polar coordinate system r and angle theta can be obtained geometrically. Therefore, the following relations give the transformation from polar to rectangular coordinates. X is equal to r cosine theta and y is equal to r sine theta, which follows the standard trigonometry rules. So, transform rectangular coordinates to polar coordinates. So we can transform rectangular coordinates to polar coordinates in two ways. One, by squaring and adding x and y, shown as here, which is x squared plus y squared equals r squared cosine squared theta plus r squared sine squared theta is equal to r squared times cosine squared theta plus sine squared theta, and that equals r squared, or r is equal to simply the square root of x squared plus y. Or we can also do it by dividing y by x. So we get y divided by x is equal to r sine theta divided by r cosine theta, which equals tangent theta. So theta is equal to the inverse tangent of y divided by x. Therefore, the following relations gives the transformation from rectangular coordinates to polar coordinates. Theta is equal to the inverse tangent of y over x, and r is equal to the square root of x squared plus y squared. So absolute value. Now the modulus or absolute value of a number x is represented by the absolute value x. For real numbers, modulus replaces the negative sign if present from a number. For complex numbers, a plus jb, the modulus is given by a plus jb is equal to the square root of a squared plus b squared. Now, geometrically, the modulus of complex numbers represents the distance from the origin 0 to the point representing the complex number on a complex plane, or the absolute value of z is equal to r for polar coordinates. Now, polar form. Using the value a equals r cosine theta and b is equal to r sine theta, a plus jb can be rewritten as a plus jb is equal to r cosine theta plus j times r sine theta, which equals r times cosine theta plus j sine theta, where r is equal to the square root of a squared plus b squared, and theta is equal to the arctangent of b divided by a, which is the polar form of r angle theta of the equation. Now, Euler's formula. Euler's formula states that for any real number theta, e raised to the j theta is equal to cosine theta plus j sine theta, where e is equal to 2.71828, which is also called Euler's constant and is the base of the natural logarithm. Ln. It's an irrational number, so using this relation, we get a plus jb is equal to r times e raised to the j times theta. Now, algebra using Euler's formula. It's a lot easier to multiply and divide complex numbers in this form. So if we let r1 times cosine theta 1 plus j sine theta 1 and r2 times cosine theta 2 plus j sine theta 2 be two complex numbers in polar form, Well, for multiplication, we get that same expression is equal to r1 times e raised to the j times theta 1 times r2 times e raised to the j times theta 2. And that simplifies down to r1, r2 is equal to e raised to the j of angle theta 1 plus angle theta 2. And that simplifies down to r1, r2 times cosine of theta 1 plus theta 2 plus j sine theta 1 plus theta 2. And for algebra, using the Euler's formula for division, we get r1 times cosine theta 1 plus j sine theta 1 divided by r2 times cosine theta 2 plus j sine theta 2 is equal to r1 times e to the j theta 1 divided by r2 times e raised to the j theta 2, and that equals r1 over r2 is equal, r1 over r2 times e raised to the j times theta 1 minus theta 2. And that simplifies down to r1 over r2 times cosine times the theta 1 minus theta 2 plus j sine theta 1 minus theta 2. Now, algebra using Euler's formula for exponentiation. So we get r times cosine theta plus j sine theta raised to the n is equal to r times e raised to the j theta raised to the n. And that simplifies down to r raised to the n times e raised to the j times n times theta. And that equals r raised to the n times cosine of n theta plus j sine n theta. Okay, so it gets kind of complicated and kind of tricky. So spend some time and just try and wrap your head around that. So when do we use polar coordinate systems? Well, usually when complex numbers are multiplied, divided, exponentiated, or have taken its roots, the polar form is more preferable. Now, how would we know when to use the polar coordinate system? Well, polar coordinates are expressed in terms of distance and anti-clockwise direction of point r and theta, angle theta, with respect to the positive axes. Sometimes it's convenient to express coordinates in this form. For example, if we were to extract y from equation x squared plus y squared is equal to 25, we get y is equal to plus or minus the square root of 25 minus x squared. Now, this is double valued with the plus and minus and not typically nice to deal with. But if we use polar coordinates, we get r is equal to 5, and it's independent of angle theta, making it more preferable and simple to work with. So let's walk through an example. Let's evaluate the given complex number and express it in rectangular form. So the complex number that we've got is 5 times cosine 50 degrees plus j sine 50 times 2 times the cosine of 40 degrees plus plus sine 40. Now, if we use the following formula from page 19 of the NCEES Supplied Reference Handbook, which we discussed earlier, of R1 and R2, we get R1 cosine theta plus j sine theta times R2 cosine theta plus j sine theta 2. And that equals R1 times R2 times cosine of angle theta 1 plus theta 2 plus j sine j sine of angle theta 1 plus the angle 2. So that simplifies down to 5 times the cosine of 50 degrees plus j sine 50 times 2 times the cosine of 40 degrees plus sine 40 degrees, which ends up being 5 times 2 times the cosine of 50 plus 40 plus j sine of 50 plus 40. So that simplifies down to 10 times the cosine of 90 degrees plus j sine 90, which simplifies down to 10 times 0 plus j, or 10j. Okay, so what's next? That's the end of the lesson for today, but for additional content, now remember, members get access to the full lesson plan download. Now, it's not just this, it's not just a PDF of the PowerPoint presentation. It's an actual full-blown lesson plan content, so be sure to check that out if you're a member. Also, I've got 3 additional sample problems for more practice for you on this topic, so also check that out. And if you have any further questions, let me hear them in the comments below. I love making these videos, and I want to try and make these as beneficial as possible. So please give me your feedback so I can make these videos better. Please like and share them if they helped you out. I would love to help grow this community, so please share them with your engineering friends so we can help make the most educated engineering community out there. So thank you so much for watching, and I'll see you in the next video.